Hello, dear students. Welcome to Digital Learning DCE. Myself, Jayashree Patta, Assistant Professor, Department of Mathematics, Maharani Science College for Women, Bangalore. In session 11 of group theory, we are going to learn about inverse of a function. Consider a permutation f of degree n on S. Since f is a 1, 1 and onto, its inverse exists and is also a permutation of degree n on S. And this inverse of f is called inverse permutation of f and is denoted by f inverse. That means here we have to take a non-empty set S, a finite set S, and if we have the permutation f of degree n on this set S, which permutation will be 1, 1 and onto. When the function is 1, 1 and onto, its inverse also exists and is also a permutation of degree n on S. That means the inverse of this permutation, which is both 1, 1 and onto, when the inverse exists, which will be also a permutation of degree n on S. And this inverse of f is called inverse permutation of f, and that we are denoting as f inverse. This is the symbol for inverse of a permutation. And here, how to find the inverse permutation of the given permutation. Suppose if you take this f inverse as the inverse of the permutation f, then if we just interchange the rows of the permutation f, then we'll get the inverse permutation. That means in the given permutation, you have to just interchange the first and second rows, then we'll get the inverse of that permutation. For example, here we have the permutation f whose elements are 1, 2, 3, 4 with the images 2, 3, 4, 1. Then to find the inverse of this permutation, which we are denoting as f inverse, is equal to what we are doing? We are just interchanging the first and second rows. See here, the second row elements, what we have 2, 3, 4, 1 will become the first row elements, and the first row of the permutation f we are writing as the second row of this inverse. So the rows are interchanged to get the inverse of the permutation f here. Now f inverse contains 2, 3, 4, 1 and their images as 1, 2, 3, 4. Now what we'll do, we'll rearrange this in some order of first row. That is what, instead of 2, 3, 4, 1, which are in order, not in order, we'll write in order as 1, 2, 3, 4. And here the image of 1 is 4. So that we'll write in the second row. And image of 2 is 1. Here I have written, and image of 3 is 2, 4 is 3. That we have written. This is what, just we have rearranged the images of the elements of f inverse. Okay. So we have here image of 1 is 2. This is what we have. Image of 1 is 2 and image of 1 is 2 in the permutation f. Image of 2 is 3. Image of 3 is 4 and image of 4 is 1 in the given permutation f. Since f is 1, 1 and onto, therefore the inverse of this permutation exists. Hence, the images of elements of the permutation f in inverse will be inverse of f will be f of 2 will be 1. Here, image of this 2 in f inverse is 1. That we have written here. Then f inverse of 3 is 2. F inverse of 4 is 3 and f inverse of 1 is 4. What the elements what we have written here, for each element its image in f inverse. Hence, we can write the f inverse permutation as 1, 2, 3, 4 and their images. So inverse of a permutation is very easy. You can just interchange the rows of the given permutation, then we'll get the inverse of that permutation. And if we observe here, if you take the composition of F and F inverse, already we have learned in the previous session how to find the composition of two permutations. So here we have the two permutations F as well as F inverse. If you find the composition of F and F inverse, similarly, you can have F inverse composition F. That is F into F inverse or F inverse into F. You will get that as the identity element itself. So the composition of a permutation and its inverse gives you the identity permutation. That we are writing as F composition F inverse is equal to F inverse composition F is equal to I. Next we have the theorem here. Theorem on the composition of two permutations. Let S be a finite set containing distinct elements. Then the symmetric set of all on permutation of degree n on S forms a finite group of order n factorial with respect to composite of permutations as the composition. That means we have a finite set of distinct elements, that is S. Then if you take the symmetric set of all the permutations of this set S of degree n, then that forms a finite group of order n with respect to composite of permutations as the composition. That means we have to show here the composition or the composite permutation on S is a group. That we have to prove here. And we know when we have a non-empty set, when it becomes a group, it has to satisfy the four axioms. That is, if you take G comma star as a non-empty set with the binary composition star, then we say G comma star is a group if it satisfies the four axioms, which are closure law, associative law, existence of identity element, and existence of inverse. If these four axioms are satisfied, then we say that non-empty set G with the binary operation star is a group. This already we have learned in the previous class. Therefore, in the same way here, we have to show that this finite set S with the composite permutation will form a group. That means again we have to verify here all the four axioms for this non-empty finite set S. Okay. Therefore, in the proof, if we take let S is equal to A1, A2, A3 and so on up to AN. We have a finite set S and the symmetric set, the Sn contains n factorial elements. And we shall show that the composite composition on Sn satisfies the axioms of the group. That is what I told you. To become a group, it has to satisfy the four axioms. In the same way, the composite composition on this finite set Sn, we have to verify these four axioms: closure law, associative, existence of identity, and existence of inverse. So now we'll see one by one. First one I have taken a closure law. What that closure law says, suppose G is a non-empty set, and if A and B are the elements of that G, then A star B also belongs to G. That we have to show. In the same way here, I have taken F is the permutation which belongs to Sn. And similarly, one more permutation G I have taken. G is a permutation on the symmetric set Sn. Because we have to show here the composite of compositions forms a group for the group finite set, symmetric set Sn. Okay. Therefore, we have to take two permutations F and G on Sn. Then F as well as G is a 1-1 mapping of S onto itself. That is, F and G are the two permutations, means from the definition of permutation we know it must be 1-1 and onto, and therefore we can write their composition as F composition G is also a permutation of degree n on S. Here, when you compare this with the group G comma star, our star is the binary operation. For this theorem, it is a composition of two permutations. Hence here, when we have F and G are the two permutations on the set Sn, and their composition F composition G is also a permutation of degree n on S. Therefore, we can write here F belongs to Sn, G belongs to Sn. That implies F composition G belongs to Sn. That is what we write. If A belongs to G, B belongs to G, then A star B also belongs to G. In the same way here, F belongs to Sn, G belongs to Sn. That implies F composition G also belongs to Sn. Hence, we can say that Sn is closed under permutation composition. Then we'll see the associative law, second axiom. Since the composite composition on mapping is associative, so it is associative in case of permutation also. So if you take the composite composition of permutations on the symmetric set Sn, then their associative is also possible in case of permutations. So that is what it is satisfying the second law, which is associative law. Then third one, existence of identity. Already we have learned identity permutation where the elements will be having the images itself. Suppose ABC are the elements of the permutation F, then the image of A will be A itself, image of B will be B itself, image of C will be C itself. That is what elements will be having images itself only, then that is the identity permutation. That we have already learned in this previous session. Therefore, the identity permutation here, what we have written, I is equal to A1, A2, A3 up to AN, and their images will be, image of AN will be A1, and image of A2 will be A2, A3 will be A3, and so on, AN will be AN. It is an identity permutation in the symmetric set Sn. Is the identity for composite composition on Sn. Then for if F is the permutation with elements A1, A2, A3 up to AN, and the images are B1, B2, B3 up to Bn, then we will see the composition of I and F. That is I composition F. What we are getting, I have written the identity permutation here, and composition is nothing but the product I into F, and then write the permutation F, what we have here. Then if you take the product of these two, the composition, which is nothing but I composition F is equal to F of A1 of F of I of A1 and F of I of A2, like this. If you take the images for all the elements, that we are getting as image of A1 will be B1, image of A2 will be B2, and so on. But this is what? This permutation is nothing but our F itself. So we are getting is equal to F. Hence, I composition F is equal to F. That is, when we multiply any permutation with the identity permutation, we are again getting the same permutation itself. Similarly, you can verify F composition I, which is also is equal to F. Hence, we are getting here I into F is equal to F, or F into I is equal to F. That means this I becomes the identity permutation on Sn. Therefore, we can say there is an existence of identity permutation on the set Sn. That is what the third axiom also satisfies here. Then we'll see the existence of inverse. Fourth axiom, corresponding to each permutation F in Sn, the permutation F inverse. Already we know the inverse of a permutation. When the permutation is given, we can find its inverse by interchanging the rows of that permutation. So here we have the permutation F in Sn, whose elements are A1, A2, A3 up to An, and the images are B1, B2, B3, and Bn. up to Bn. Then if you take the inverse of this, that is what? When you interchange the rows of this F, which we are getting as F inverse is equal to B1, B2, B3 up to Bn with the images A1, A2, A3 up to An. It also belongs to Sn, and that becomes the inverse of F. Therefore, the inverse for each permutation exists in Sn. Hence, we can write that Sn is a existence of inverse in the finite set Sn. That is, F composition F inverse is equal to F inverse composition F is equal to I. This we know already, we have done in the inverse of a permutation, and here the composition of permutation with its inverse we are getting as a I. That is what in group we have learned. A star B is equal to B star A is equal to E. If we are getting as an identity element with the binary composition on an element and its inverse, then we say that the inverse of an element exists. In the same way here, we are getting the composition of F and its inverse, we are getting it as a I, the identity permutation. Therefore, here all the four axioms of group are satisfied. That is, closure law satisfies, then associative law satisfies, and the existence of identity permutation is there, which is I. And also we have the inverse permutation for each permutation in Sn. Therefore, we can say that Sn is a finite non-abelian group of order n factorial, which is nothing but here that Sn, which is a symmetric set, forms a group with a binary composition or the composition of two permutations. This is the proof of the theorem. Next, we'll see some examples, exercise we have here. If F is the permutation, one permutation, and G is another permutation, then we have to find here F inverse and G inverse. F inverse we know already. I have told you the definition of inverse of a given permutation. When F is a permutation which is both 1-1 and onto mapping, then the inverse of that permutation exists. And the inverse of that permutation we will obtain by interchanging the rows of the permutation. In the same way here, in this example, what they have given? They have given two permutations, F and G. You have to find the inverse of F, one example. That is, just interchange the rows of this F. Similarly, you find the inverse of G by interchanging the rows of this G. And the third question here, you have to verify F composition F inverse is equal to G composition G inverse. You can write here composition or F into F inverse also you can say is equal to I, where I is the identity permutation. Whether this condition is satisfying or not, you have to check. When you obtain your F inverse and G inverse, take the composition of F and F inverse and find whether it is equal to the identity permutation or not. Similarly, other example, second example here, two permutations F and G are given. Then you have to find F inverse composition G. So first what do you do here? You first find the inverse of the permutation F, which you will get by interchanging the rows of this F. Then take the composition of that inverse function F with the elements of the permutation G. That is what you will get F inverse composition G. Similarly, the third example again here, they have given two permutations F and G. You have to find F inverse as well as G inverse. And these are the some references which you can refer for further study or to understand the permutation in better way. So in this session, we learned here inverse of a permutation, the definition, and then how to find the inverse of a permutation. And one property or one condition you can say here, a composition of a permutation with its inverse. It will always gives an identity permutation. That is what we have given here as a node. F composition F inverse or F inverse composition F is always identity permutation. Then we proved one theorem where when we have a symmetric set Sn with n of order n with n factorial elements, then the composition of permutations of that Sn forms a group. That we proved here, or where you have to verify all the four axioms of group. The four conditions what we have: closure law, associative law, existence of identity, and existence of inverse. If all the four conditions are satisfied with respect to permutation composition of Sn, then we can say that Sn also forms a group under composition of two permutations. Then we learned some examples here, how to find the composition of two permutations as well as their inverse, and some examples. And also you can refer the following textbooks to solve some more examples, or you can understand the permutation in a better way. Thank you.